Hello, everyone. I'm Kelly Werner, and I think we should just get started because we have kind of a tight schedule today for today's pitch competition. This is the ANS Student Webinar Series. This is the third and final portion of the Student Webinar Series. It's our senior pitch design competition. And we'd like to thank our sponsors, the ETWD, the Education Training and Workforce Development Division, and the Young Members Group. They graciously sponsored the prize money for all of our student participants. As I said, I'm the SSD chair. We have been putting this series on kind of in lieu of the postponement of the 2021 Student Conference. It's been postponed to next year. It's still being held at NC State, and our 2022 Student Conference will be held at University of Illinois Urbana-Champaign. So everything's just kind of postponed a year with all the craziness going on. We'd also, at the very beginning of this, because we had to postpone the student conference, we were not able to announce our SSC Accommodation Award winners. And these winners are some of our nominees. There's 18 applicants, and we picked 5 winners. These are students who have who've been recognized by advisors and other ANS members as outstanding members of our community and have gone above and beyond for ANS. This year there's 3 graduate students and 3 undergraduate students. So we send these people kind of a congratulations for being awesome. It was very competitive, and it was kind of hard to pick just a few people out of this list. So our graduate student winners are Ashita Trivedi, and she goes to NC State. She's also helped organize this webinar and all the other webinars. She's the student co-chair for the NC State conference. Amanda Bachman, she goes to University of Tennessee, Knoxville, and then Seth Kilby is at S&T, Missouri S&T. These are all great people. Send them a congratulatory email or Twitter or something, since they weren't able to be recognized in person at the conference. We had 2 undergraduate winners, Alexandria Ragsdale and Mackenzie, Warwick. These 2 are also extremely involved in the society and have done a ton for their student sections. I know they're all really, really great people. So congratulations to our winners and to all the nominees as well. You're great. And with that, I'm going to start introducing how our sorry, had an issue with that. Our competition will be ran for today. So how this worked is we reached out to all the graduating seniors who were not able to present at the student conference, and had them say if they would like to present their senior design summaries or have that had been accepted to present at the student conference. So these are papers that had already been submitted and approved. We wanted to give them a chance for ANS to kind of see all the hard work they did this year. There was a lot of submissions, but of all the submissions, we chose the top 10 to give us a pitch of their student design and their student projects at their different universities. So each team for today will have 6 minutes for their pitch, with 1 minute allowed for follow-up questions from our judges. There also will be a 1-minute bell, so if you hear an alarm, that's just letting them know they have a minute left before they need to kind of wrap things up. And so don't worry about it. We had 5 judges who graciously volunteered to score and review each of the presentations. And they're from all over the ANS spectrum of technical fields and policy fields. The top 5 winners will receive, first place is $1,300, second is $1,100, third is $900, fourth is $700, and fifth is $500. So thank you again to WDD and YMG for supporting this. And with that, I'll introduce our 5 judges. So we have, first off, we have Elise Huffman. She works on the clean energy policy as a professional staff member working on the energy subcommittee of the House Science, Space, and Technology Committee Majority, where she worked as the 2019 American Association for the Advancement of Science Congressional Fellow sponsored by the American Nuclear Society. Prior to the fellowship, Elise worked as a reactor core designer for the Oconee Nuclear Station and also performed fleet-wide spent fuel pool criticality safety at Duke Energy in Charlotte, North Carolina. Elise received her MS and BS in nuclear engineering from the University of Florida and is a licensed professional engineer in the state of North Carolina. So thank you, Elise, for being one of our judges. And our next judge is Kathryn Pratt. Kathryn Pratt is the vice chair of YMG and has been involved in ANS since 2012. Kathryn earned her bachelor's and master's degrees in nuclear engineering from Penn State University and began her career in the nuclear industry working for Westinghouse Electric Company in Pittsburgh. Her job with Westinghouse has taken her around the world, from the first AP1000 power plants in Sannam, China, to her current position supporting initial plant testing of the AP1000 units at Plant Vogtle in Georgia. So thank you, Kathryn. Our third judge is Dr. Nicholas Stauff. He is a principal nuclear engineer at Argonne National Laboratory and has expertise with advanced reactor design and methods development. Thanks, Nicholas. Our fourth judge is Dr. Dave Pointer. He's a PhD in nuclear engineering from the University of Tennessee in 2001, a master's in nuclear engineering from University of Tennessee in 2000, and is the leader of the Advanced Reactor Engineering Group and distinguished R&D staff member of the Reactor and Nuclear Systems Division of Oak Ridge National Laboratory, where he specializes in computational fluid dynamics and heat transfer, experimental fluid dynamics and heat transfer, and nuclear reactor safety. So thank you, Dave, for being on today's meeting as well. And last but not least, we have Harsh Desai. Harsh works at the Nuclear Energy Institute as a senior manager. Harsh is responsible for financial modeling, economic impacts, policy development, business strategy, and data analytics. In his previous role at the Department of Energy, he was an advisor to the Technology to Market Director, focused on commercializing clean energy technologies through innovative programs and partnerships between the national labs and private industry. Harsh has previously served as the ANS Congressional Fellow working for a U.S. Senator. He has also worked at the Naval Nuclear Laboratory and at GE Hitachi Nuclear Energy. Harsh has an MBA from the New York University, along with a BS and MS in nuclear engineering from NC State University. Harsh is an active member of the American Nuclear Society, and he is my ANS counterpart as the chair of the Young Members Group. The Young Members Group and SSC has been trying to work a lot more closely this last year to really, how can we partner together, and Harsh has been a great asset for that and a really, really awesome ANS member. Harsh enjoys going on adventures such as chasing tornadoes, being an avid photographer, traveling, and brewing beer. So thank you to all of our judges again. This really wouldn't have worked if you guys hadn't also agreed to help. So next we will start our presentations. As I said, each person will have 5 minutes before a bell goes off, and they'll have 1 more minute to finish their presentation, and then a minute for follow-up questions assigned from every judge. After all the presentations, we'll have feedback and tabulate all the scores and declare our winners. So with that, I will switch over to our first team, the Salty Spittoon from North Carolina University. And we can get this. Okay, and this is Vincent Navellino and his team from NC State. So go ahead and take it from here, Vincent.
Alrighty, so the project that I worked on for my senior design was the design of a fast molten salt reactor. And to give the motivation behind why this project, the National Reactor Innovation Center has set out an aggressive timeline to roll out advanced reactor technology over the next decade. This culminates in their final goal of having a non-LWR demonstration reactor by 2030. Our group proposes a design of a molten salt reactor to meet that goal. Historically, demonstration molten salt reactors, such as the molten salt reactor experiment and the aircraft reactor experiment, were thermal reactors that used fluoride salts and used graphite moderator. Our design is different in that it uses a chloride-based salt, and it does not include a moderator and is a fast reactor. In order to meet the deadline of deployment by 2030, we identified a couple goals that our design needs to be. It needs to be small and economical, so cheap to build, as well as low power as well. And the reason for that is because we do not hope to produce electricity with this design, but simply demonstrate the fast molten chloride technology. So I give a picture to the right showing a CAD model of our reactor vessel. And to walk through that design, our design is a little bit over 7 feet in diameter and a little over 15.5 feet tall, made of HT9 steel, approximately 1 inch thick. In addition, we include a stainless steel reflector on the outside, and that reflector serves to shrink the size of the reactor core, as well as is the main way we control reactivity in our system. So during normal operation, we would have a hydraulic lift the reflector pieces into place or about the core midplane. The reason why we split the reflector into 4 pieces is because if for whatever reason the reactor needs to be shut down and one of those reflector pieces gets stuck up, we have verified through calculations that we'd be able to shut down the reactor with 3 of the reflector pieces down. In addition, we also use 19.5 atom % enriched HALEU fuel. We chose this particular enrichment because it gives us the best economics, so it's the cheapest reactor cost for our design. This was chosen through a parametric study that we conducted by looking at various reactor fuel enrichments as well as cylinder diameters. Our particular mixture for our fuel salt uses 33%, 67% UCl3 NaCl. And this particular concentration corresponds to the eutectic concentration for UCl3 NaCl. This is important because this is the minimum melt temperature for that system. So we are able to lower the average temperature of our reactor down, thereby extending the lifetime of our vessel because of lower thermal stresses, because of lower operating temperatures. In addition to the vessel, our design also includes a few unique 2 molten salt reactor auxiliary systems, one of which is drain tanks with a freeze plug. And so the freeze plug acts to stop the flow of salt when the temperatures are within operating and design ranges, but will unfreeze, allowing the entire primary system to be drained into the drain tanks. The drain tanks are engineered to be subcritical when full of the fuel salt mixture. And this happens without operator interaction, hence it's a passive safety system. We also include a fission gas removal system, which allows gases like xenon-135 and krypton to be removed from the reactor, and this serves 2 purposes. The removal of xenon allows us to reduce the amount of excess reactivity that needs to be loaded into the core, and the removal of radioactive gases such as krypton reduces the overall radionuclide makeup of the salt and thus reduces the radioactivity of the salt for safety reasons. We also include a salt chemistry control system, and this functions as the main way that we add fuel to the reactor during operation, as well as the main way we control the chemistry of the salt to reduce corrosion to the various components during operation. So to talk about the overall cost for our reactor is about $380 million, and this comes under the budget of $500 million that we have identified. We calculated this cost by looking at so the initial fuel loading cost, construction cost, engineering cost, and estimating those, and then the cost of financing. So we assumed a 1% interest rate on the loan and 10-year lifetime for the project. The ultimate source of funding would be from the United States government allocating the funds to build a reactor. And one of the results that I show is to the figures to the right at the bottom right-hand corner. And this is the results from our one of the results from our parametric study showing the decreasing cost of fuel as we increase enrichment, as well as the cost of just the fuel for our particular case, which is the 7 diameter foot case. So I want to thank you all for allowing us the opportunity to present and share our senior design project. I would like to open up the opportunity for the judges to ask their questions.
Great, thank you, Vincent. I think, Nicholas, this was a question that, or this is the one of the presentations that you agreed to prepare a question for. So if you would take it from here.
Yes, good morning. So my question is, the design will be a demonstration reactor. So what type of technologies do you envision to demonstrate, and what type of unique testing capabilities will it enable? And how did you account for testing requirements in the design process?
Thank you for that question, Nicholas. So for our design, for a demonstration reactor, some of the things that we included in the design is on the secondary side, it would allow us to test multiple different secondary salts to be used because we specified for our initial design lead chloride, but whatever salt was compatible with the components would allow us to test various different secondary salts. In addition, the technology we're looking to demonstrate is the fast spectrum molten chloride technology. So as salt mixture itself is made up of strictly chloride salts, which have never been demonstrated before. Within the design process, that's one of the reasons we have the 3-loop system, is that we have a secondary salt loop, which allows us flexibility with choosing what we use for the secondary salt, and then the tertiary loop that I identify in that system diagram in the bottom left corner is going to be water cooled to ultimately inject heat to the environment.
Thank you very much.
Oh, great, thank you both. Thank you, Vincent, and good job. We're going to be moving on to our next presentation. This is these presenters are from the University of Michigan and are presenting on the feasibility of silicon carbide fuel cladding for SMRs, and this is Team Millennial. So go ahead and take it from here, Tommy.
We need a new scale modular reactor. So why do we need a new cladding, right? Current cladding is made out of zircaloy 4, and when it reacts with high temperature steam, it liberates hydrogen readily, and with given enough temperature, it could detonate, such as the picture you could see in the top left corner from Fukushima in 2011. Silicon carbide has a much lower hydrogen release rate than zircaloy. It also promises high strength and also a higher melting temperature comparable to that of the UO2 fuel itself. So that's why it's promising for an accident-tolerant fuel cladding material. The reason we're investigating the cladding material for a new scale small modular reactor is that it's promised to be cheaper to build and cheaper to operate. And INL is actually contracting NuScale to build 12 of these for their joint use modular plant project. And so given these reasons, we're investigating the use of silicon carbide cladding. And from NuScale, we obtain our requirements shown in the center. First requirement is that the failure probability has to be less than 10 to the minus 6, or a million, hence our team name. And that's obtained from the data for zircaloy fuel cladding after one cycle of 2 years. The second requirement is that the fuel cannot melt at maximum linear heat generation rate of 21.3 kilowatts per meter that we have obtained for the critical heat flux limit for the reactor. And to model our design to see if we meet those requirements, we use Ben Belgason's MATLAB code as shown in the bottom left corner in the modeling methods. And it takes into account of the thermodynamics, the irradiation effect, and the material mechanics of the cladding material. And we run the simulation on both the average linear heat generation rate expected for normal operations at 8.2 kilowatts per meter, as well as the maximum of 21.3 kilowatts per meter. So all in all, our design is shown in the center, As you can see, our proposed design has a slightly greater radius, is a slightly thicker cladding itself, and a slightly thicker pellet cladding gap. And all of that is to account for the stress and the pressure involved in the cladding itself. The cladding material is made out of SA3 QIC 150A 66 composite silicon carbide. It's made using chemical vapor infiltration. It has a fiber architecture of 0 degrees and 90 degrees 2D braiding, as you can see in the picture in the bottom. It allows for the ductility that is not apparent in monolithic silicon carbide. It also has a pyrolytic carbon coating on the fibers itself, so that it could increase the fracture toughness of the material. And so after running our simulations, we're shown on the right-hand side stress development over the 2-year cycle, as well as the failure probability associated with those stresses. So on the stress plot, you could see that the tensile stress is dominant in the inner radius, and compressive stresses are dominant in the outer radius. And indeed, the tensile stress continues to increase, so that would be the main focus of our mechanical failure probability. And the other thing is that you could see that the azimuthal stress has a greater increase than the axial stress over the lifetime. And that is partly because of the higher pressure dependence of the azimuthal stress versus the axial stress to fission gas release. But all in all, the maximum stress is still below the proportional limit stress of 163 megapascals, indicating that the cladding is unlikely to fracture over the lifetime. And so to calculate the failure probability, we have an equation using Weibull statistics to get that probability value. And it's strongly stress dependent, as you can see in the equation. In the sigma naught, which is the characteristic strength, and m, the Weibull modulus, are material dependent parameters that fit the probability. So on the probability plot, you could see that the axial probability is less than 10 minus 6, so that meets our first requirement. However, the azimuthal probability exceeds 10 minus 6 towards the end of the cycle, and that is reflective of the stresses developed by the examined in the previous plot. And so in conclusion, our centerline temperature of 1681 Kelvin is less than the melting temperature of Euro 2. It's competitive with the current design of using zircaloids, and it's safer in a loss of coolant accident. And the next step of our design would be to minimize the azimuthal stress by reducing fission gas pressure. And there are several ways to do that. One is to reduce the power of the reactor so that there are less fission reactions to occur. And the other way is to modify the composition of the fuel pellet itself so that less fission products will be produced. We could also add a outer monolith to increase the strength of the cladding. And this is the end of our presentation. Thank you so much for listening to us, and we'll look forward to any questions that you have.
Great, thank you so much, Tommy. So I think, Dave, would you please take the question here?
So I really wish we had time for a more extensive conversation, because this is a really interesting work. I would like to ask about the confidence in your prediction of failure probability. You know, one of the challenges in looking at advanced fuels is really in cladding materials is really the shortage of experimental data to adequately quantify the material properties and performance under different operating scenarios. Can you comment on what you think the biggest source of uncertainty in the projection of failure probability might be?
Right, of course. So the probability itself is it's empirically determined, especially for the parameters used in calculating that probability. We have looked into different parameters as well, but from literature review, we have determined the best parameters for our specific silicon carbide composite design. Understandably, the confidence could be affected by changing those parameters. However, looking at the axial stress limit and the axial driven probabilities, we across several different sets of parameters that we have used, it continues to be below the 10 to the minus 6 limit imposed by Zircaloy. So we're confident about the axial-driven failure probability. It is the azimuthal failure probability that we have concerns about, and that's why we aim to tackle that by using various methods that could reduce the probability of failure, which is not reflected by Y-blue statistics solely. And that includes strengthening the cladding and also reducing the pressure within the pellet cladding gap.
Thank you.
Thanks.
Great, thank you very much, Tommy and Dave. Our next up, we have presenters from West Point Academy. It's Ricardo Damiani, and he is with the team Army Nuclear Power for Land Operations. So go ahead and take it from here, Ricardo.
Alrighty, thank you for that introduction. So the purpose of our project was to design and test safety measures for the future implementation of nuclear power in the U.S. Army's land operations. So our motivation for this project was the need for power in deployed environments is very high. The reality is that the cost of 1 gallon of diesel fuel in a deployed environment can be up to $400. And the real cost comes in the casualties that we sustain from convoy operations. Most of the casualties since our involvement in the Middle East have come from convoy operations, and a majority of these convoy operations are for fuel transportation. So the Deputy Chief of Staff of the Army, G4, wants to eliminate the need for constant fuel transportation. So the goal of this project was not to build a reactor. However, we needed to model a reactor in order to test the safety parameters for implementing mobile nuclear power. So to do this, we modeled a Holos 13.5 megawatt electric generator. And although the winners of the design competition for the Army were BWXT and Westinghouse, this doesn't really matter because all of the reactor proposals had to meet the following requirements. It had to fit in a standard 20-foot shipping container, weigh less than 34,000 pounds for transportation in a C-17 aircraft, produce at least 10 megawatts electric of energy, and use tristructural isotropic fuel containing high assay, low enriched uranium. So to accomplish this task, we had to do a few things. We had to measure dose rates outside of the reactor area, model cool down period for emergency shutdown procedures, analyze possible physical damage to the reactor, and optimize mobility. So our proposed reactor area is as follows. The reactor will fit in a standard 20-foot shipping container made of stainless steel. For shielding, we're gonna use also 20-foot stainless steel shipping containers lined with 18 centimeters of borate polyethylene on each side. And we wanna use 1 container per side on the reactor housing and 1 on top to protect against vertical threats. The cost of each shipping container for shielding is estimated to be just under $25,000 and weigh about 30,140 pounds, which gives us a comfortable factor of safety when meeting the weight requirement. So to protect from horizontal vehicular threats, we propose to have a tank ditch around the reactor and the shielding containers, because this would limit the capability for enemy vehicles to go and attack the reactor directly. Finally, the whole area would be barricaded by 8-foot concrete barriers, commonly known as T-walls or Texas barriers. So the next step, now that we establish our parameters for the reactor area, was that we had to assess battle damage threats because it will be used in a forward deployed environment. So given our proposed reactor area, vertical threats such as mortars were the only realistic threat to the reactor's physical safety. So we modeled a shipping container in SolidWorks and found that the shipping container would easily withstand the peak overpressure caused by 82 millimeter mortar round without yielding. However, the primary concern is a threat of rupturing after several blasts from different mortars or different weapons. So now we established the parameters for the reactor safety. We had to also account for human safety and the safety of all the workers that are going to be around the reactor. So the final neutron dose equivalent outside of the reactor area was found to be 5.3 plus or minus 2 millirem per hour, which this creates the need for us to use engineered controls, supervision, and regulation to ensure soldier safety and prevent any possible health issues. Additionally, we recognize the possibility of needing to conduct immediate transportation within 24 hours of reactor shutdown due to the nature of where these mobile nuclear reactors are going to be used. Since they're going to be in combat zones, we need to be prepared to move the reactor within 24 hours to prevent it from falling to enemy hands and to prevent further proliferation concerns. So for this, we recommend that for a hasty shutdown, we need an external high negative reactivity control rod that can be inserted into the reactor, but is not organic to the reactor in order to meet the weight requirement. So this will be the manufacturer's responsibility to ensure that the reactor can take an external high negativity insertion mechanically. Lastly, for environmental considerations, our group developed a computational spreadsheet to determine soil activation by isotope based on neutron flux. This will be very useful when determining site safety after moving the reactor. In closing, I'd like to leave you with our recommendations. To maintain transportable shielding, we cannot afford to build permanent structures if we want to maintain our mobility, which is the purpose of the mobile nuclear reactor. We need to conduct physical kinetic attacks on the assembly because although we've done calculations and run models, theory doesn't always apply to reality. And lastly, the designer needs to implement safety parameters such as high negative reactivity control rods to insert into a reactor for emergency shutdown procedures. And these procedures need to be rehearsed before deploying the reactor to a combat zone. With that, I'd like to conclude my presentation and open up the floor for any questions. Thank you for your attention.
Great, thank you very much, Ricardo. Harsh, you're up.
Hey, Ricardo, thank you very much. Thanks for a great presentation. I do want to tell you that this is a huge area of interest, especially between national labs, universities, and among various different vendors and even utilities as well. So kudos on the work you have done. Let me ask you this, especially for the mission that this would be needing. One of the things that we have to really focus on is flexibility of the power plant, ability to go up and down in power, and making sure that you have maybe not even power, but other needs that are required. So can you walk me through if you guys looked at that, and if so, what were some of your conclusions and recommendations?
So as stated before, the main purpose of this project wasn't to build the reactor. It wasn't to develop the physical reactor itself. But I'd like to address a few of those concerns. As far as flexibility, because not every base has the same power needs. But mainly, this reactor can serve several purposes for the Army. And one of them could be to power remote, isolated places. And another one could be to provide large amounts of energy needed for some of our new weaponry, such as our lasers that can be used for missile defense purposes. And so we didn't really look for power flexibility. However, we did look at our ability to shut down the reactor and move it immediately in the case of any external attacks, which has to do a lot with power flexibility because this reactor needs to be able to go from producing 22 megawatt thermal to immediate shutdown and transportation while maintaining worker safety. So that was a big area of concern, and that's why we are really focusing on the emergency shutdown mechanisms. And once this is being implemented, we need to rehearse the procedures to ensure overall safety. And we're also looking into modified vehicles to move the reactor with some extra shielding to protect drivers.
Great, thank you very much.
Thank you.
Our next team is also from NC State. Our presenter is Amadou Turanka, and they are presenting on high enrichment, high burnup loading pattern optimization for a 2-loop Westinghouse PWR. So with that, I'm going to take it from here.
Thank you, Kelly. It is a really long name. The goal of our research is to optimize a highly enriched loading pattern for a tool with mouse PWR that meets some predetermined NRC safety standards and is economically viable with a 24-month fuel cycle. Typically, reactors use 5% enriched fuel as per NRC limit. In this case, the max spin burn-up is limited to around 63,000 megawatt days by NTU. But if a highly enriched fuel is used, a safe higher burn-up can be achievable. And with this higher burn-up, there is more efficient fuel utilization, which means there's more depletion, and meaning there's going to be a waste reduction and an extended cycle length. With the extended cycle length, there is less outages compared to 18-month standard cycle length, which means the reactor can increase the capacity factor and it can be economically more efficient. So this research will basically how to design the loading patterns, and we did everything using ANC. So ANC is a software by Westinghouse, which is just an advanced nodal code that basically uses two-group nodal diffusion theory to calculate core parameters of interest. So if you look at the bottom right of your screen, you can see the loading pattern that we designed. In order to design this loading pattern, we used a lot of vulnerable absorbers and pins because we use just 5% and 6% enriched fuel in this case. Although we could have gone up to 7%, we just decided to stay low to 5 and 6%. We used vulnerable absorbers in order to flatten power profile and to increase power density and provide margins for thermal limits in the reactor. So you can see we tried to gain a design from the L3P loading pattern design with the ring of fire design on the inside. We know there's a push in the nuclear industry right now to increase the reactor core life. So with this design, we used more of the burn fuel on the periphery of the core. So that will reduce the leakage to the core barrel. So that means there's less nutrient irradiation to the core barrel, which can increase the life of the core. So that's just like another economic factor that will factor in to make our research more viable. And the top left-hand corner, the primary core considerations, just basically shows you all of the, like some of the main nutrient limits that was set on us. Of importance is the rod insertion limit speaking factor. That was set at 1.66 for us. And we're using a two-loop reactor, so it's a little bit difficult to bring down the power peaking factor in this case because for a two-loop reactor, it's smaller and there's it's less symmetric, so there's a less placement of the fuel. So we have to be very we have to come up with a really good design to basically move the fuel around, and we use around 56 fuel assemblies, which is less than the limit that was given to us of 60. And on the right, you can see the safety considerations that we were supposed to meet. We considered two cases: the hot zero power in starting of the reactor, and the hot full power for the beginning of life and end of life cycle. And you can see we meet all of the criteria that was given to us with this loading pattern. So the most important thing to look here is the max burn up at hotspots and also the maximum ejected rod walk. And our loading pattern meets all of those. And on the bottom left-hand corner, you can see the economic analysis for this loading pattern. Down at the bottom right, you can see the price for this loading pattern is around $5, which seems low because that just considers the price of megawatt hour for the loading pattern. It does not really factor in the building of the core or operational cost. We usually just assume that it's $25 operational cost. We take this up to around $30, which is still less than the $25 average limit for nuclear reactors. And so in just short summary so far, we just showed you can, with using higher enriched fuel, like more than the 5% NRC limit, we successfully met a 24-month extended fuel cycle length. We met all the safety criteria, which means the this field design and the highly enriched and the high enrichment means we still show that it can be safe. You can operate a reactor safely with a higher enriched fuel, and we also show this is more economically viable. A goal for this research is to show that you can with using higher burn-off, we can increase the burn-off, the pin burn-off. So there's like more fuel utilization, just like a better fuel utilization. And we just hope this research helps push the industry more into research of using highly enriched fuel because of the benefit it provides in just like longer cycle and higher fuel utilization. With that, I'm just going to thank you guys for listening to me, and just going to open the floor for questions.
Great, thank you very much, Amadou. I guess we'll just let the judges take this from here. Do we have a question? Let me see.
Can you hear me? This is Elise. Thank you for your presentation. It is really fascinating. As a core designer in a previous life, I enjoyed it. I was hoping you could explain to all of us a little bit more about any limitations to the analysis that you've done. Specifically, if you can touch on the economics and if you looked at, how a changing market, I know that fabrication and the price of uranium fluctuate a lot, so I was wondering if you could talk to any limitations there as well. Thank you.
Thank you, Elise. That's a good question. So this research was done with from my mentors at Westinghouse. So they provided us with a spreadsheet. They gave us a bunch of field costs. So we did went out and check the field cost, but we just used the Westinghouse field cost that was given to us in our spreadsheet. That's what we used here. The price seems low for the fuel for the price per megawatt hour, but that's just a consideration for just the loading pattern. It does not involve, because if you look online for the average fuel the average price per megawatt hour for nuclear energy, it's around $30. It's around like $35. This just shows for the loading pattern. But if you want to like include the operational cost and the cost of the reactor, we can just include around $25. That takes it over to $30, which is still considerably less. And yeah, so like one important thing. So you also asked about the core considerations. One important thing we were worried about was the rod insertion limit speaking factor. And because this is a small reactor, it was a little bit difficult to get that down to the accepted value. So we just have to like use the blocks of like the bondable absorbers and just try to even out the power picking factors and just get like a clean, even power density to provide margins for thermal limits. Sure. Thank you.
Great, thank you so much for that. And we'll start our next presentation. This is from NC State, presented by Patrick Hartwell. There's the Hot Rods, there's their team name, and he will be presenting on optimization of a 2-year PWR fuel cycle utilizing Formosa and Prism.
Our goal for this project was to produce a 2-year loading pattern to satisfy a set of constraints listed on Table 1 in the lower left-hand section. Beyond that requirement, we were tasked with running a comparison between results for manual optimization using Framatome's core simulator Prism with NC State's fuel optimization program Formosa. This was desirable for a few reasons. First and foremost was the reduction in downtime for a reactor, changing from Framatome's standard 511 effective full power day cycle to a 686 full power day cycle reduces the downtime by 192 days over the course of a 40-year reactor lifetime. When it comes to manual optimization, the main advantage our group has had over a previous group with similar objectives was the inclusion of additional burnable poisons in some of our cross-sectional data. Because the 2-year cycle is longer, it requires a higher reactivity content from the loading pattern This resulted in what was confirmed to be too much reactivity for Framatome's standard 32 GAD-bearing pins per assembly to be able to handle, and required increasing that limit to 44 pins per assembly. Once we had those cross sections, we were able to produce a satisfactory loading pattern by a manual optimization using Prism. Once we reported our success, Framatome provided additional constraints that we also met, such as a restriction on how many enrichments we could use for assemblies in a core. You can see there are 6.20% and 5.95% as fresh assemblies only in the upper left-hand core loading pattern. So after we had that loading pattern, we were able to analyze it for cost assessment using a proprietary assembly analysis program from Framatome to determine the cost of the loading pattern per core. Comparison against the financial analysis of a preceding group is in Table 2, and it revealed a $5.22 million improvement due to a 0.25 to 0.5 weight percent enrichment reduction to most of the assemblies in the core. Optimization with Formosa uses a simulated annealing algorithm which mimics cooling process of a metal and converges to an optimum solution in around 12 hours by narrowing the range of acceptable objective functions. This is basically a weighting function that allows us to look at the first results that diverge from our desirable cases, and then perturbs that loading pattern until it moves closer and closer to the best case possible. You can see in the upper right-hand graph the progression from number of cooling steps or changes in perturbation. From the initial point to the end, it dramatically changes. So, in order to compare the results obtained through manual optimization with Prism with results obtained through running the Formosa optimization code, we had to understand the difference between the reactor simulators. In the lower right hand, you can see the comparison between their flows. Framatome uses a whack-a-mole program to basically just run all possible versions of the core, feeds that into feeds that into Prism using a proprietary version of Casmo to generate the cross sections for their assemblies, and then assesses it with FuelRQ. We made significant progress to replacing Simulate in that process for Formosa because the cross sections from Framatome's proprietary version of Casmo were not available to us to insert into Simulate. So it became not quite coherent. Using the same reactor loading pattern with the same assemblies with Simulate data for Formosa resulted in a different core. So that would result in different results. In order to circumvent this, we decided that we would need to couple the Formosa optimization code directly to Prism to get accurate results for comparison. We've made significant progress with coupling Prism and Formosa as we have successfully edited and recompiled the source code with Prism being executed in place of Simulate. Currently, we are working on converting the simulator output parsing scripts to index Prism summary files so that we can replace the entire function of Simulate with Prism. We're looking forward to being able to compare the optimization results from it being coupled with Prism to our manual optimized core in the next few weeks. In summary, we've successfully created a 2-year loading pattern that satisfies all of the constraints provided at a lower cost than the previous design groups. We've created the framework for finishing coupling the programs for our project and for future continuations, such as expanding the coupling to allow for the optimization of any Framatome reactor. Thank you.
Great, thank you very much. We'll take questions now from one of our judges.
Great. Thank you so much for that presentation. Again, very interesting to me as a previous core designer, and it's funny you guys use Formosa because that was something that I looked at using for a graduate project once upon a time. So I'm glad to see it's still alive and kicking. One question I had for you, when we looked at using Formosa in real life application at the utility I used to work at, although it could create an optimized pattern that did meet all the criteria like you guys were able to do, and it could do it quicker than maybe a core designer could, the core designer could always be Formosa in terms of optimizing it further to create a lower cost. So I'm curious here if you had any discussions with the vendor on a path for like a real world application.
We discussed it as Formosa is basically a predecessor for any of the loading patterns that they would want to consider and further refine after Formosa has given the output. If they can present a reactor, get a starting point from Formosa for comparison, and then the neutronics analysts can take it further, then that just saves them the time for getting it up to that point that Formosa does.
Thank you.
Great, thank you. We'll move on to our next presentation. It is Project OLS from the United States Military Academy at West Point, presented by Sally Varner and her co-authors. Go ahead, Sally.
So thank you. Good afternoon, ladies and gentlemen. Once again, I am Cadet Sally Varner, and on behalf of Cadets Cameron Brinson and Gregory Smith, myself, and Colonel Chad Schools, I thank you for this time to present to you our Capstone research project. So the purpose of our work was to characterize the use of an organic liquid scintillator, or OLS, for a field deployable multiplicity counter that would allow first responders to rapidly determine if an unknown neutron source contains special nuclear material. A multiplicity counter uses the neutron emission timing to characterize a source. In other words, the neutrons emitted from an alpha neutron source will have a different timing signature than neutrons emitted from a fission source. This requires many synchronized detectors operating independently to provide accurate timing. Current multiplicity counters are generally based on helium-3 detectors, making them expensive and heavy due to a required moderator, resulting in a loss of timing information. The proposed detector, on the other hand, would provide a low-cost option, not to replace current systems, but to provide an affordable multiplicity counter that could be more widely fielded with local authorities and first responders. The concept drawing in the top left corner shows how the tubes filled with the liquid scintillator could be arranged to lay around an unknown neutron source and act as an independent detector, providing the accurate event timing required for multiplicity counting. Using a liquid scintillator as the active volume provides the advantage of being able to measure fission energy neutrons directly from the source without the need of a moderator. However, the potential of a single neutron being counted twice as it elastically scatters from one tube into another tube, as shown in the bottom left figure, remains to be a disadvantage. Double counting neutrons could adversely affect the system's multiplicity counting performance. To determine if double counting would be an issue, we designed and built an experiment that compared the neutron detection in a 5-centimeter section of the OLS-filled tube with and without two additional adjacent tubes, as shown in the figure in the lower left. We hypothesized that an increase in detected neutrons in the center tube when adding two adjacent tubes would indicate that neutron double counting was occurring due to elastic scattering. These two configurations were also modeled in MCNP6 for comparison. Before I cover our results, though, I would like to highlight some of the things that we accomplished and learned along the way. We realized that it takes many steps to build a radiation detector. 2 years ago, I had the opportunity to test several commercial handheld detectors during a summer summer internship at Oak Ridge National Lab, and I gained some insight into how complex detectors can be. While our detector probably will not be commercially available for some time, we were able to design and 3D print a detector housing unit shown in the bottom right image that held the 64-channel photomultiplier tube, its electrical connectors, and properly aligned the OLS tubes to the channels. We filled and capped 8 Teflon tubes with organic liquid scintillator following appropriate safety measures. We assembled and collected data using a 14-bit 250 megasample per second digitizer. Because we used californium-252 and other radioactive sources, we were sure to follow principles of ALARA to minimize our exposure to the radiation. We placed our setup in a light-tight box with a californium-252 source about 25 centimeters away with an intervening lead brick. We chose californium-252 because it is a spontaneous fission source producing neutrons with a similar neutron energy spectrum to that of special nuclear material. The top center plot shows the results from our collected experimental data. The plot shows no distinguishable difference between the center tube response with or without additional tubes in place. This suggests in our configuration, double counting scattered neutrons will not be an issue. Additional measurements with various trigger levels and longer collection times are required to confirm these findings. In the lower plot, our MCMP modeling does show an increase in the neutron flux on the center tube when the adjacent tubes were present. This increased neutron flux is from lower energy neutrons, as would be expected due to elastic scattering in the adjacent tubes. Although this does present a potential concern for the overall multiplicity performance of the system, it does not necessarily contradict the experimental findings of these low energy neutrons may have been undetectable at our experimental trigger level. Again, additional measurements would be required to further clarify the findings. So some of our future plans for this project include: 1, improving and stabilizing the optical coupling between the OLS tubes and the PMT face. 2, optimizing the design to an 8-tube holder so that 1 tube can be placed across each of the 8 rows of the PMT. And 3, improving the MCMP model to track the energy deposited in the OLS. This concludes my presentation. Once again, I thank you all for taking the time to listen about our research project, and I now yield this time to any questions you may have.
Great, thank you, Sally. Let's open up the floor for questions from our judge.
Hi, good morning. So thanks a lot for the presentation. It's really interesting project. So I'm not very familiar with a synthetic scintillator technology. Could you explain us why you need different scintillators tubes instead of one large? Because this is really what is prompting your research.
Yes, so thank you for your question. Our big thing is that this would be used in a fuel deployable sense. So that concept drawing in the top left corner really gives a great idea as to how it would be used when there is this container that, say, is on some sort of convoy and it's suspected to have some sort of special nuclear material in it. So you can take what would eventually be the tubes of OLS and you can throw it over the container, and based on the characterization from the neutrons emitted, you could tell whether or not there is special nuclear material in the container or not. Sir, does that happen to answer your question?
Yes, thank you very much.
Great, thank you very much, Sally. Moving on to our next presentation. This is Group 7 from North Carolina State University, presented by Jennifer Jeffcoat.
Just to give a little background history on our project, in the late 1960s, DOE launched the California 252 production campaign utilizing 90 targets. The production campaign was abandoned shortly after, just about a year. 86 of those targets, however, continue to be exposed to the high neutron flux environment in the K reactor. Upon decommissioning, 21 of those targets was recovered by Oak Ridge National Laboratory. The remaining 65 targets was then stored at Savannah River Site in El Basins. Currently, Savannah River Site holds 80% of the world's heavy curium and plutonium-244. In the remaining 65 targets, that was initially from the California production campaign. The purpose of our project is to create a computational model based off the iteration histories to produce a prediction of the mass concentration of the isotopes remaining in each target. Two methods was considered for our design. So the first method was to group the targets together, and then that will give multiple targets the same isotopic concentrations. Or we would use model 2, which would be to analyze each 65 targets separately, one at a time. Majority of the designs, specifications, and geometries was classified based on our computational model on calculated assumptions and parameters, such as the pitch, the enrichment, and geometry outlay. However, the irradiation histories of the targets and locations of the drivers was provided to us. If you look below at the PowerPoint, figure 1 on the left-hand side is a map of the K reactor at SRS. The core is a hexagonal lattice of annual driver assemblies, and the assemblies is moderated by heavy water. The 6 coolant loop helps create the high neutron flux environment. We made assumptions for the enrichment of the uranium alloy, which is about 90% enrichment, due to knowing that they underwent high enrichment. The modeling of the Mark 18 drivers geometry was assumed from the Mark 14, 16, and 22 drivers. As shown in figure 2, the middle figure within the PowerPoint, this is the geometry layout for Mark 14, 16, and 22. Due to the drivers being replacing the first cycle of the Mark 18A targets, we decided to assume that they have similar geometries to the Mark 18, consisting of 3 inner rings. The first inner ring consists of a mixture of aluminum and heavy water. The next 2 inner rings consist of enriched uranium alloys, and the outermost ring is just aluminum by itself. The darkest ring is the cladding. The target is known to be 4 feet in length, and the drivers is known to be 6 feet in length. The one interesting thing about figure 1 is that our core was, the dimensions of our core was unknown. So we decided to go with model 2 of our computational analysis. So that way we was able to generate a flux distribution for figure 3 based off of the placement of the drivers instead of the entire core itself. Utilizing scale and origin, our assumed geometries was placed along with the materials of uranium and plutonium and heavy water. Due to its very low cross-section of aluminum, we initially neglected it within our material section of our script. The burn data from the irradiated histories was included along with the timetable. And the timetable was added so that way we can take into account for the different amount of fuel within each driver by changing the density. Our model analysis helps predict the isotopes of Californium-252, plutonium-244, and heavy curium such as 244, 245, 246, 248, 250. For figure 3, this is an over-exaggerated view of the flux distribution we assume from calculations and a known peak factor of 1.35, leading us to identify the power level of each assembly at each cycle. Our major challenges for our project was producing outputs that would converge. Most of our outputs was diverging due to assumed geometries. We found our density to be too small. To fix this issue, we decided to add the aluminum material back into our model. So our model is predicted to not be accurate due to our geometries being different from the actual geometries from not given to us because it's classified. So if you was to replace it, then the data would become more accurate. But however, we are expected to generate a higher resolution due to the fact that we decided to do target-to-target analysis for our computational analysis. This concludes my presentation. I'll be open for questions.
Great, thank you, Jennifer. Judges, do you have any questions?
Yes, hi. Thank you so much for your presentation. It's really fascinating, and you know, you can tell you guys put in a lot of work on it. I just want to take a step back and, you know, from a higher level, I'm curious, you know, I understand where this material came from, how it was produced, and I understand your problem statement about wanting to understand the quantities that are in there. But why do we want to know that? Like, what is the application? What is the purpose of understanding what's in there, and what are they going to do about it? Thank you.
Okay. So heavy curium is not a naturally produced element, so you can only get it from reactors that's already been operated. And the uses for these isotopes, it could be used as a neutron source, or you can basically use them in industrial and scientific operations and discovering new heavy elements, or using it in metal detectors. So these are why that these isotopes are important, and they can also be used in the medical field.
Thank you very much.
Great, thank you, Jennifer. Our next presentation comes from the University of Michigan. This is the University of Michigan Senior Measurements Team, presented by JT Icavetta. And I'll let you take it away, JT. JT, I think we're having a hard time hearing you. Are you still on the line?
Oh, yeah. Is it good now?
Thank you. Yep, we can hear you now.
All right. Thank you, Kelly, for the introduction. The development of nuclear weapons devices remains one of the gravest dangers in the world today. As well, safety must also always be assured in the precise art of arranging fissile materials. Nuclear emergency responders are interested in finding, identifying, and quantifying special nuclear material. Each of these instances presents the problem of finding the reactivity of a multiplying system. Reactivity cannot be directly measured, but we can estimate reactivity using Rossi alpha measurements, and we are specifically looking at organic simulators as they've shown promise in evaluating fast systems. This senior design project focuses on developing an organic simulator system for Rossi alpha measurements by analyzing organic simulator features and optimizing the detector geometry structure. So as you can see in the top right center, these are three different major parameters that we evaluated. So that's geometry, simulator material, and then the operation feasibility optimization. So through each of these three parameters, we were able to develop a figure of merit. So this evaluated for geometry, the efficiency, the number of detectors, the cost, crosstalk concerns, and then the orientation of these detectors. For the material, we're looking at the need for pulse shape discrimination, as additionally the cost, and then the light output of our simulator material. And then we're also evaluating the lower energy threshold. So from these three figures of merit, we selected the highest value of each. So below that, you can see three plots. That is our figure of merit for each one of these three different areas. We evaluated a couple of different configurations, as you can see in the lower left-hand corner. These are some examples of configurations evaluated. So we evaluated 7 different configurations with dual array, so 3x4. We looked at ring geometry, 4x3, and then we changed the number of detectors as well, varied from 16 up to 50. Looking at this, we modeled a couple of different ones where we were looking at a weapons-grade plutonium alpha phase source reflected by 3 inches of either copper, iron, nickel, or tungsten. And then we evaluated whether we were able to actually pull away some Rossi alpha plots. So that lower center plot is our Rossi alpha plots that we were actually able to get from some of our models, as well as we did actual data analysis using actual materials. And our Rossi alpha plot, that negative exponential decay that alpha value of that negative exponential decay is actually our alpha value, and we can use that to estimate reactivity. And we're able to get some pretty accurate results. With our final design considerations, we were able to find accurate reactivity estimates. And so these design considerations are placement detectors at 108 degrees, best mitigates that neutron crosstalk. The dual array configuration with 24 detectors, seen in that bottommost example detector arrangement, was the best due to a combination of accuracy and measurement time. We found that the alpha value was invariant of the lower energy threshold, as well as organic scintillator was the optimal scintillator material due to highest light output and lowest cost. Additionally, we were able to find that pulse shape discrimination was not necessary for this application, and that was pulse shape discrimination, was not needed for the configurations that we evaluated. And so with that, I'd like to thank our mentors on this project, Dr. Sari Putzi, Mike Hua, ANS and YMG for this opportunity to present, and go blue. So I'll open up the floor for questions now. Thank you.
Great, thank you, JT. We'll open this up for our judges.
Hey, JT, thank you very much. This is a fascinating presentation that you put together. And I'm sure we can spend an entire webinar just talking about this topic. But let me ask you this. It seems like there's a lot of various ways you can go about this. But what were some of the challenges that came by? It occurs to me that you probably ran into several of them. So can you walk me through some of those?
For some challenges for our project, is that your question?
Yeah.
So I think one of our biggest challenges was actually dialing down our figure of merits. And so our actual design, how we were going to use this. And so I think our biggest thing was making sure that this was something that could be used in a field setting, something that was easily disassembled, something that was easily able to be transported, while also getting the best resolution out of our detectors, but also minimizing the cost. So I think that's why we have a couple of figure of merits that you can see there. And so I understand that sometimes all these figure of merits might look confusing, but it's because we evaluate each little aspect of our detector to make one really great system. Does that answer your question?
Yep, thanks.
Great. Next, we have a presenter, Jordan Crowell, from their team name is One Energy from Ontario Tech University, and I'll turn it over to you, Jordan.
Hello, everyone. Most Canadian Arctic communities use diesel generators as their primary source of electrical power since they're not connected to any major electricity grid. According to Natural Resources Canada, the price of non-subsidized electricity can be as high as $1.14 per kilowatt hour, which is much higher than most Canadians are paying for electricity. The objective was to develop a reliable zero carbon emission source of combined electricity and heat for Canadian Arctic communities that is more affordable than current diesel generated power. The approach was to use a micronuclear reactor combined with Stirling engines to drive the electrical generators. The reactor can provide both heat and electricity. It has the following features: graphite moderated since it doesn't freeze in cold climates, fuel channel design, CANDU style fuel bundles due to them being proven technology, and CANDU bundles have 37 elements with 4 rings. Lead 208 coolant because it would allow higher temperature and hence increase thermal efficiency, and it didn't increase in volume when it freezes. Lead 208 also has a lower neutron absorption cross-section. Finally, Stirling engines were used to reduce the number of components and have a direct power conversion cycle. The first design requirement was that each fuel element, as you can see here, would not exceed a linear heat rating of 450 watts per centimeter, since reactors have a maximum operating rating between 420 and 460 watts per centimeter. The second design requirement was that the reactor was capable of producing 4 megawatts electric to power the average Canadian remote community. It was named after my Aunt Suzanne West, and hence the Zanfori reactor project was born, which you can see here on the left of your screen. Based on NASA's Stirling engine research, Stirling engines can obtain efficiencies in excess of 40%. It was assumed that the combined efficiency of the Stirling engines and the electrical generators is 40%. As a result, the ZAN-4E needed to produce 10 megawatts of thermal power. Neutronics calculations were carried out using lattice calculations to generate 2 group cross-sections using Serpent, which is a Monte Carlo code, and a 2-group diffusion formula to calculate the core K effective. Various pitch lengths for a 2D CANDU fuel assembly were simulated using Serpent to determine how it affected the effective multiplication factor. A pitch of 35 centimeters was chosen since it allowed for the largest increase in the multiplication factor per unit change in cost for nuclear grade graphite. The resulting core height and diameter were 1.7 meters and 2 meters respectively. A thermal hydraulic analysis was performed to determine the centerline fuel temperature of the middle assembly of the reactor, as well as the axial bulk coolant temperature profile in the fuel channel, as can be seen in the plot labeled fuel centerline and coolant temperature. The maximum fuel temperature is below the melting point of uranium dioxide. The ZAN-4E has inherent and passive safety features by having the core cool itself through the natural convection of lead-208. The change in pressure due to the change in density of the lead at the top and bottom of the reactor needed to be large enough to overcome the pressure losses throughout the reactor. Various fuel channel diameters were analyzed, and it was determined that a diameter of 11 centimeters was sufficient to allow for natural convection cooling to occur. An 11-centimeter fuel channel is approximately 6.4% larger than a typical CANDU fuel channel. As a result, the CANDU fuel bundle used in the ZAN-4E needed to have its ring spacing increased by 6.4% to allow for natural convection to occur, as can be seen in this 3D printed cross section. The next task was to determine the necessary amount of enrichment needed to maintain criticality for at least 2 years. A 2D model of a ZAN-4E fuel assembly was simulated in Serpent with an enrichment of 19.5% weight uranium-235 to provide the maximum reactivity possible. Burnup was then simulated to 30 megawatt days per kilogram to identify at what point the core would become subcritical. Serpent produced 2 group constants for each burnup step. They were then used in the equation shown in the top right hand of the slide to find the effective multiplication factor for the entire reactor core. It was assumed there was 70 milli-K of negative reactivity from systems, structures, and components that needed to be overcome. Even with the negative 70 milli-K considered, the ZAN-4E was capable of maintaining criticality for up to 2 years and still had plenty of margin to be run for longer, as shown in the plot labeled available positive reactivity versus burnout. As a verification step, a 3D Serpent simulation of the entire core was also performed and shown to produce K-effective values that were sufficiently close to those calculated using the 3D diffusion approximation. The image is labeled Serpent 3D model, showing visual representation of the results obtained from Serpent. Finally, a 1/13th scaled down model of the ZAN-4E was constructed as a way to show some of the physical phenomena in the ZAN-4E reactor. These include the capability of Stirling engines to use heat and convert it into mechanical energy, the ability of natural convection cooling to occur, and how different fuel channels produce different amounts of power. The model was filled with water, and cartridge resistance heaters were used as a way to stimulate the fuel bundles that would be used. There's lots of work still to be done, but I believe that the ZAN-4E reactor can be a fantastic solution to the climate and energy crisis that many Canadian remote communities are facing. Thank you, and I will now accept and welcome your questions.
Great, thank you, Jordan. Open the floor for questions.
Hi, it's Jordan. Just wanted to thank you for your presentation. It's really impressive the amount of work that you guys have done, and you know how far along in the work that you guys are. I wanted to talk a little bit about the applications and if you've given consideration to the conditions in which these reactors are. So we're talking about Arctic applications, and does the ambient temperature outside being, you know, what it is up there, does that have any negative impact? I'm thinking more like that the temperature delta between the high temperatures in the reactor and the very cold temperatures outside would lead to, you know, further aging faster. Maybe is that something you guys considered?
That's a really great question. Material properties and kind of more environmental conditions like you're talking about weren't considered as in detail at this stage of the process, but the next stage is to start identifying a transport system up to these communities and start doing environmental assessment of, okay, at this operating temperature, what does it look like? What things we need to think about? At this operating temperature in the dead of winter at -50, what does that look like? So it wasn't considered, but it is in the next stage of the process for sure. It's a great question.
Okay, thanks.
Great, thank you, Jordan and Kathryn. We'll move on to our last presentation. This is Team Rad Bot from West Point, presented by Brendan Hewline. And go ahead and take it away, Brendan.
All right, thank you. So the purpose of Rad Bot is to detect and localize hazardous radiation sources in an indoor environment in order to provide the user a better understanding of the situation. So if a user is tasked with maybe cleaning up a radiation incident or inspecting a facility, they want to know, is this facility safe? Can I reduce my protective posture? And where are these radioactive sources inside the facility? So as you can see in figure 1, there are several subsystems on our robot, and these were worked on by an interdisciplinary team of students. So we had nuclear, mechanical, electrical, systems engineers, and also computer science majors. Myself and Cadet Kaylin Mays were the nuclear engineering majors on this group, and we were primarily focused on the radiological detection aspect, which is the design and integration of a detector array on the robot. This can be seen on the front in figure 1. So our full system consists of the detector array of sodium iodide gamma detectors, which provides source directionality and localization data. There's a LiDAR on the robot that will map the indoor environment as the robot drives through hallways, rooms, obstacles, things of that nature. Then the detector data will be overlaid on top of the LiDAR, so it gives the user a map of the facility they're going into and where the radiation is. There's also a camera to allow the user to drive this, and it's powered by a 50-meter tether, so it's not relying on battery power, and there's a data relay, so we don't have to worry about Wi-Fi or infrared signal getting lost in any of this. So like I said, we focus on the detector array design, which can be seen in figure 2. That is like a footprint. This is an array of 5 gamma ray detectors, and it's self-occluding. This means the principle behind this, if there's a source on the left side of the array, the left side detectors will receive higher count rates than the right side, so we know that the source is on the left side of the array. There are 4 exterior 2 by 4 by 6 inch sodium iodide scintillators. These provide gross counts and some medium energy resolution spectroscopy. There's also one interior cylindrical 3-inch diameter by 3-inch tall sodium iodide detector. What is novel about our design is that the interior detector is depressed. It sits lower than the exterior detectors. This, we believe, will allow us to get better angular resolution than simply having all the detectors at the same height, and will allow us to get directionality in the Z. If you just had a square of 4 detectors side by side, you'd get good directionality, a good angle measurement in the same plane. However, as the source goes higher, you're unable to get that Z directionality. When we have a depressed detector in the middle, as the source gets higher, as is the case in using a robot that's close to the ground, then you eliminate more and more and more of the interior detector, giving us a unique signal response, which is critical. We have had some promising test results, which can be seen in figure 3. In figure 3, we took a radioactive source, we put on a track and moved it at constant velocity from front to rear. So front being where detector 1 is, rear being where detector 3 is. This track was about 1 meter to the right of the array, so on the side of detector 2. The signal responses from each individual detector are seen in the plot. As you can see, detector 2 has the largest signal response as the source is closest to this detector. Detector 1, seen in the blue line, peaks earlier. Detector 3, the green line, peaks later. This makes sense as the source passes by detector 1 first and then detector 3. What is very interesting about this plot, though, is the bottom purple line, which represents the signal response of the interior detector, detector 5. As you can see, there are 2 humps in this signal response. This is because there's a lack of occlusion or lack of self-shielding from the detectors between detector 2 and detector 1 and detector 2 and detector 3, these corners. This is actually a very important part of our design, as at that position of the source, we're able to get a more accurate reading, a better signal response due to this lack of occlusion. In conclusion, we have had some test results that show that this detector array does give unique signal responses, and we believe will result in an improved angular resolution as compared to a square detector array. And that is what we are currently working on, we'll be working on towards the future. So we want to place sources and move them on the track circularly at a distance of about 1 meter from the array. And we want to do this from 0 to 360 degrees, so we get a signal response at every angle. We will then be able to compile these signal responses and create an algorithm out of this. It is a complicated process and is the ultimate goal of our project. But so far, we've shown that we're able to get an array online and a sample of signal responses that show a promising result for future work. Ladies and gentlemen, this concludes my presentation. I'm opening up to questions now.
Great, thank you very much. We'll open the floor up to our judges for questions.
Hi, Brendan. Really thank you for your presentation. I think it's really interesting, and I like the thought and the explanation about the different geometries. I had a question about the test setup and if it was representative of how the Rad Bot would work if it was actually moving. So I found it interesting that you did not move the Rad Bot past the source to obtain the same data. You chose to move the source past the Rad Bot. And I'm wondering, especially just given how sensitive some detectors are, that, you know, any kind of movement as this thing is rolling across the ground, if that would create additional noise or would somehow obscure data, and if that is the reason behind, or maybe you could talk to the reason behind moving the source rather than the detector.
Yeah, thank you for that question. So the primary reason why we moved the source past the detector array is because this system right now is being worked on by an interdisciplinary group. So we have people working on the tether, working on the LiDAR, working on everything, and it's a pretty big robot. So we didn't want to take time away from our fellow students who are working on other aspects just to test the detector array. We decided, hey, we're going to test this on its own first, and then later we can do a final test, actually moving all the systems at once. So this was sort of a subsystem test to determine the usability or unusability of this detector array.
Okay, thank you.
Great, thank you very much. All right, we will now kind of add up our totals. Then we're also going to just leave a tiny bit of time for some feedback from judges. We don't have time to get to all of them, but if judges would give a little feedback while Ishi and I take a moment to look at the scores.
Sure. Should I get started on the first presentation?
Yeah, let's just go for a couple while we count.
Sure. So on the presentation on design and economical low power fast spectrum molten chloride reactor, I really appreciated the it was a very good presentation, a very nice slide that summarized it very properly. And so thank you for this presentation and for the work on the project. I don't have anything to propose to improve the presentation. I think you did an exceptional job. However, so your team put a lot of work on this project, tackled a few key design issues, and brought a few innovative solutions like the external hydraulically positioned reflector. It would be nice also to highlight the TRL of this technology, the technology readiness level. Obviously, there is a lot of additional technical work that remains to be done on all of these topics because you guys are attempting to design a full reactor. So maybe it would be nice also to better frame the boundary of your particular study. But otherwise, I wish you the best for this project, to you and your team.
Thank you, Nicholas, for that feedback.
Hi, I don't think we can hear you, Elise.
Sorry, I was going to say I can give additional feedback if we need more time, but if not, go on ahead with.
We're just waiting for responses from a couple of the judges, so when that comes through.
Okay, so I'll just give a little bit of feedback. I guess, you know, the two different presentations that I asked questions on regarding core design. I don't have, sorry, the list in front of me, so, but you guys know who you are. I would encourage you to take a look at the bigger picture and try to understand more about how economics really drives the decision-making in a core design. Obviously, you need to meet all the parameters, and you guys proved that you could do that, and it's very valuable to go through that exercise. But the main decision, you know, that why we choose a design over another is usually driven by economics. So trying to understand that piece more thoroughly would really help with your application moving forward and any discussions that you have with vendors. One specific piece of feedback I had for I can't remember his name. The presentation using Formosa. It was a little confusing to me in your presentation. Like I knew the goal was to create a design meeting those design limitations, but you also spent a lot of time discussing the integration of the various codes and how they could work together. And so I wasn't really sure what the main objective of your project was. So if you present this in the future or just as a tip moving forward, clearly state your goal and wrap it to get back together. Thank you.
This is Dave Pointer. Can I just add that I think I'd like to applaud all of the people who have participated in today's program, for being willing to adapt and participate in a video environment, which is much more challenging than giving your presentations face to face, where you have immediate feedback from your audience and you can see when things aren't clear. I think you've all done an exceptional job putting together your materials for the presentation, and also it's very clear that everybody's invested a lot of time in preparing the remarks so that you can stay on time and be very efficient in your use of your time. I think most of our presenters have done a good job of walking through a logical path of discussing the purpose and then the approach and the methodology used, followed by some discussion of results and conclusions. So it was very easy for us to see all of the hard work you've put into these design and R&D activities over the past few months. So congratulations to all of you for the good work that you've shown to us today.
All right, thank you for the feedback. Go ahead, Kathryn. Sorry.
Oh, sorry. If we're good, we're good. See the results. I just wanted to echo what Dave said and just say from YMG that we really appreciate everyone coming on today and presenting their work, and for the fact that we've had so many participants that have stayed throughout the whole presentation. That even though we've gone over time, I think is really indicative of how interesting all of the different projects were.
Thank you, Kathryn. All right, since we are almost 10 minutes over, we're going to announce the winners through email. I apologize for that. There's just been some kind of issues with scoring this and getting all the results tabulated quickly. So thank you all again for presenting today, and thank you for all your hard work. We'll announce this through an email to all of ANS and probably privately to all of you students who presented. So thank you guys so much. Don't forget, there's a few more webinars put on by YMG on April 15th and on April 30th. Both of those are spotlights on national labs, one for Idaho National Lab and the other for Argonne National Lab. So keep an eye open for those. With that, I will conclude the webinar, and thank you all so much for joining.